Hey everyone, we're going to start a new lesson tomorrow, and I wanted to try it out on video first. So what we're going to do is solving systems of quadratics, just like what we did in Unit 6 when we did linear functions and solving systems of linear functions. So we're going to do the same thing. We're going to start with graphing. I'm giving you two quadratic equations, and if we're going to do this by graphing, you have two options. You can either do it by hand or on the calculator. Probably going to learn the calculator first and use that most in class, so let's try that. Go back to our calculator, put it into y equals, say 2x squared plus 7x plus 10 for y1, and for y2 we can say x squared minus 4x plus 9. We just hit graph. So let's see our two equations. All right, notice that they intersect somewhere up on the top of around the y-intercept. So let's figure out that exact point. To do that, we have to go to our trace key, go down to intersect, which is our fifth option, hit enter. Then it's going to ask us for the first curve, and we're trying to figure out which one we're on. So once we know we're on one of the equations, we hit enter. We find ourselves on the other equation, we hit enter again for the second curve. Hit enter once more for the guess, and it'll give you an intersection point of negative 0.091 for x and y as 9.375. So we could get our coordinates as, say, negative 0.1 and 9.4. All right, so that's just the graphing method. Obviously, you can do it by hand, but the calculator is much easier. So what about this? What if we have something not quite as nice, something we probably can't graph? This is not in a form that we're used to graphing. What do we do about it? Well, in Unit 6 we learned we had a substitution method and an elimination method. In this one, because it's very easy to solve for either x or y, we're going to do substitution. Just because there's x squared, y squared, and all these other things, and it does not make it much more difficult. Just a few more steps and a few more operations. So let's first solve for y. Y is easier. Move the x over by subtracting from both sides. Divide by -1. Generally in these problems you want to solve for y because y is one we can operate less with. X we can use as our roots. Y's we have to factor to get our roots out. So y equals x. Right? We divide by -1 on both sides. Okay, so now we have y equal to x. Let's plug it back in. If we take x and plug it in everywhere y is in this equation, we should come out with something fairly useful. So we'll have x squared plus x squared plus x plus 3x plus 2 equals 0. Alright, all we've done is plug in like we normally would with substitution. Now let's combine our like terms. 2x squared plus 4x plus 2 equals 0. At this point you probably are starting to recognize what we're trying to do here. We're trying to solve for our roots, we're trying to solve for our solutions. This actually is a linear equation and a quadratic. We're trying to figure out their intersection point. So this isn't just two parabolas, this is actually a parabola and a linear equation going through it. Figure's not drawn to scale. So here we have a 0 and we have an x squared, which means we should probably use the zero factor property. You could use the quadratic formula or any of the other methods we use to solve, but I'm going to start by doing, just because it's so easy, the zero factor property. Factor out the GCF. And now I have a simple a equals 1 trinomial. So I get 2 as my GCF that I took out. X plus 1 equals 0. So my only root is going to be x plus 1 equals 0, x equals -1. Right? There's no other solution. I have an x squared from the start, so I know there's only going to be two possible solutions. If they're the same thing, this looks like one of those graphs that only intersect once. So we have x equals -1. Let's plug that into one of our original equations to get our y. Let's just choose the easier one. That'd be, I'd say, this one. So we'll say -1 minus y equals 0. Solve should be fairly easy. Add the 1 over. -y equals 1. Divide -1, y equals -1. So here we have our coordinate. X is -1, y is -1, and that is our answer. So that's solving quadratics, systems of quadratics using the substitution method. Now we did have a quadratic and a linear. That's not always going to be the case. Sometimes you will look at a problem and you'll say, I have no idea how to do this one because now I have two quadratics and I don't have a y to set equal to x, and it just seems like too much. But if you think back to Unit 6, we can use the elimination method. So if we see a 5x squared and a 5x squared on top of each other, we know elimination's got to be the way to go. So let's multiply this, let's say top one by -1. We get -5x squared minus 20x minus 9y plus 7 equals 0. Right? So all we're doing is the elimination method. Generally with problems where you see the same number and variable on top of each other or near each other with the ability to eliminate by multiplying by a number, you want to use the elimination method. In problems like the past one where you see something nice like this where you can solve for a variable easily, you'd want to use substitution. Alright, so let's try and do this now. We can eliminate the 5x squared and the -5x squared. Inverse operations go to 0. -20x and +20x can eliminate there. So let's say we have 10y squared. Combine the terms as we go down, minus 10y, and minus 60 equals 0. So this is good. This gets us to a place where, again, we can do a zero factor property. The only issue that we have is that we have y. We don't have x. So we're going to have to do a little bit more work at the end. For a zero factor property, we can take out the GCF of 10, get y squared minus y minus 6 equals 0. From here, again, a equals 1 trinomial, y minus 3, y plus 2. So then our answers for y could be 3 or -2, right? If you solve them, we set them equal to 0. Now that's helpful and all, but don't we want our x's too, and couldn't we have multiple x's for the same y? When we think about our roots, we have to think about what goes into it, how many roots we should have. For this one, we could have a variety of roots because we have both an x squared term and a y squared term. So let's plug back in and see how many we end up getting. If we plug back into our first equation, because there's just less terms here, it's probably easier to work with, we could say 5x squared plus 20x, and then if we plug in 3 for y for the first one, we'll say plus 27 minus 7 equals 0. 5x squared plus 20x plus 20 equals 0 after we simplify our like terms. Here now we can take out a GCF, take out 5x squared plus 4x plus 4 equals 0. And now we can factor that. We say 5x plus 2, x plus 2. So x equals -2. And that gives us one of our points. When y is 3, x is -2. Now let's figure out for this -2. We're going to do the same exact thing. We're going to plug it back into one of the original equations. let's pick the first one again. So we'll say 5x squared plus 20x minus 18 minus 7 equals 0. And now we just have to solve. Luckily, again, we get to take out a GCF. Take out the 5. Another a equals 1 trinomial. So we keep our GCF out here, and we say x plus 5, because the middle term is positive, so the bigger number would take the positive sign, and x minus 1 equals 0. So our two solutions for x would be 1 and negative 5. So our answers, 1, negative 2, and negative 5, negative 2. So now we have 3 possible solutions. So those are the 3 ways you're going to solve systems of quadratics. Be prepared to use them in class tomorrow.